ideal gas equation. Yeah. So there are a few assumptions that you need to make before you can assume whether a gas is ideal gas or not. Okay, so basically, if the pressure P is low enough, then you can assume the gas as ideal gas. Okay, so the opposite ataupun the real gas is what we call the real gas lah, yang those that does not follow ideal gas. So the real gas, okay, for the internal energy, I think you have learned about internal energy. Internal energy is given by the symbol U. Okay, so internal energy of a real gas is a function of P, pressure, and temperature, T. So the pressure dependency is the result of forces between the molecules. But remember again, for ideal gas, we assume that there is no force between the molecules. Okay, so because of that, for ideal gas, we can say that the internal energy U is only depends on T, temperature only. Okay, so for ideal gas, you have this equation, internal energy U is the function of T, temperature only. Okay, so it does not depend on the pressure. Okay, next. Okay, so we are going to develop some property relations for an ideal gas. When I say property, this refers to thermodynamic properties. Okay, so any parameters that related to that is related to thermodynamics. So pressure is a type of property, temperature, okay, volume, and so on. Okay, so first we have this heat capacity at constant volume. Okay, the symbol is CV. Okay. So in this case, CV is a function of T only. Okay, this is only for ideal gas, yeah? Okay, so CV is defined as, okay, remember again, I told you if you have these three lines for the equal sign, it means that it shows a definition, okay? So this CV, heat capacity at constant V, is defined as the change of internal energy du divided with change in temperature dt at constant volume. So you have this small v here. This means that the v is constant. Okay. So in the case of internal energy, in ideal gas, the internal energy is only a function of temperature. Kan? So you can write this as the normal differentiation, the normal D symbol for differentiation. So equals du over dt. And as a result, the CV also is a function of temperature only. Okay. So for the ideal gas, the change in internal energy, delta U, is equal integration of CV times dt. Okay. So similarly, enthalpy or H is a function of temperature only. Okay. You can derive this based on this definition of enthalpy. So enthalpy H is defined as U, internal energy, plus PV. Okay, so you can write U, internal energy, as the function of T only because it's ideal gas. And then from the relation of ideal gas equation, PV equals RT, you can replace PV here with RT. Okay, so again, because R is a constant, then this becomes a function of temperature only. Okay, so as a result, enthalpy is a function of temperature only. Okay. Now, you have another type of heat capacity, right, which is the CP. Okay, so heat capacity at constant pressure, CP, is defined as the change of enthalpy over change of temperature at constant pressure. Okay, because of the enthalpy for ideal gas is a function of temperature only, so you can write like this. So as a result, the CP also is a function of temperature only. Okay, So you can get this relation delta H equals integration of Cp times dt. Okay. And then we can also write the relation between Cp and Cv. Okay, because you have this relation Cp equals dH over dt. And then from the definition of enthalpy U plus PV, you can write as this du over dt plus R. Okay, so du over dt is equal Cv for ideal gas. So here you can replace du over dt with Cv, so you are left with this. So Cp equals Cv plus R. Okay, so this equation does not imply that Cp and Cv are themselves constant for an ideal gas, but only that they vary with T in such a way that their difference is equal to R. Okay, so Cp and Cv, they are not constant. They are not necessarily constant. What it means here is that the difference, yeah, if you find the difference, Cp over Cv equals R, which is constant. Only the difference is constant, which is R. Okay, so as a summary, again, for ideal gas, the internal energy is a function of T only. Okay, enthalpy also is a function of T only. And as a result, the heat capacity, Cv and Cp also, they are a function of T only. Meaning that even if you change the pressure, the values of U, H, Cp and Cv does not change, okay, at the same temperature. Okay, now, okay, so equations for process calculation. So for any system, sometimes we want to know the change in terms of the energy balance, and then the amount of work or the amount of heat, okay, from a system. So in this case, we can develop these equations for ideal gas. Okay, so for a unit mass or a unit mole of ideal gas in any mechanically reversible closed system process, you can write these two equations, okay? So the first equation is for the work here. So during our first lecture, I told you that there are two types of work. Yang pertama ialah the push-pull work. So the push-pull work is related to force, okay? But remember again, this is work related to gas, okay? And then it's a closed system process. So in this case, you don't have any movement, you don't have any mass in or mass out, okay? So you just have the substance. So in this case, the only work related here is the second type of work, which is PV work. In other words, it's only related to compression or the expansion of gas, okay? So here you have the work, equation for work is only the PV work. So dW equals negative PdV. Okay. And then another thing, you can write the energy balance, which is du, change in internal energy equals dQ, change in the heat, plus dW, change in the work. Okay. You don't have the kinetic energy or the potential energy because, you know, we are just referring to this substance in a closed system. So there is no other outside force, okay? And the system is not, you know, there's no mass in or mass out. So this is the energy balance that you will get, okay? All right, so, and here, because in the previous slide, we have the relation between CV and U, right? So you can write du equals CV times dt. So you have this here, okay? So because of this, you can rearrange this equation to bring dq forward. Okay, so you bring dq forward. So dq equals CV times dt plus pdv. So pdv, this one we replace the dw with negative pdv, okay? Right, from this equation, one equation, you can we can consider three three conditions. Okay. So first, Okay, so first is the isothermal process. What it means by isothermal process is when you have the the temperature constant. So iso means same. Okay, so thermal we refer to the temperature lah. So same temperature process. In this case, the delta U is 0, delta H also 0, and then the equation for Q, heat, becomes like this. Okay. Macam mana nak derive tu later I will show you. The second process is the isobaric process. So isobaric means same pressure, so constant pressure. So in the case of constant pressure, you have this equation. The above equation here is the general equation for delta U and delta H, right? So delta U is this one, and then delta H is this one, and then you can derive the equation for Q and W. And then another one is for the isochoric process. So isochoric here means same volume, so constant volume process. So in this case, the Q becomes equals to delta U, and then the work becomes 0. Kenapa 0? Why 0? Because remember, the work that we refer here is only the PV work. So when the V is 0, then of course you will have 0 work. Okay. So macam mana nak derive these equations is actually we can go back to this one main equation yang ini, dq ni, and then for each different processes, you can actually replace the equation, the formula for P, for example, or V or T, because this one is for ideal gas. So you have the PV equals RT equation, right? So you can substitute into the equation and then you do the differentiation or the integration to get it. Okay. So okay, so the important equations are shown here. Yeah, yang for the isothermal process, you must remember delta U, delta H 0, and then the Q is equals negative W. Okay, which is also equals RT ln V1, V2 over V1. Okay, or if you have the pressure only, then you can write in terms of pressure, negative RT ln P2 over P1. Okay, this is equation 3.27. And then for the isobaric process, the Q is equals delta H. Okay. And then the W is negative R times the change in temperature. For isochoric process, the Q is equals delta U, and then the work equals 0. Okay, this is just some derivation of the equation for the isothermal process. Yang ini saya tunjukkan. When T is constant, okay, you have this energy balance du plus dq. Du equals dq plus dw, which is equals 0. Okay. And then from here, you can derive dq equals negative dw, which is equals p dv. And then you can integrate, you get integration P dV, so you substitute P with RT over V and you just do the integration with V. Okay, so you get RT ln V2 over V1. Okay. Alright, another type of process is the adiabatic process. I'm sure you have heard about adiabatic process. So in this case, the delta Q or the dQ is 0. Okay. So for the adiabatic process, Okay, so for the adiabatic process, when you have dq equals 0, you can actually derive these equations. Yeah, so this is derived from the uh, from the ideal gas equation as well as the equation for the heat capacities. Okay, so okay, this is page 77 from your textbook. So you will get this equation. Okay, so in this case, you can integrate, you do integration to get t, okay? And finally, you can get this relation. So in this case, we have this new parameter, which is the gamma, and defined as the ratio between Cp and Cv, okay? So for the adiabatic process, Tv to the power of gamma minus 1 is constant. And then for Tp, you have this term here, okay? 1 minus gamma over gamma is constant. And then for the PV, okay, PV power of gamma is constant. Okay, and then we can also derive the equation for work. Okay, for work, okay. So for the adiabatic process, one thing to remember is that the heat capacities are constant, yeah, because there is no heat in or heat out. So the heat capacity become constant. So that's why you can do the integration with assuming that the CV or the CP are constant. Okay, that's why you can get this CV. You consider it as constant, so you just get this delta T here. Okay, and then you can write this in a form of gamma. Okay, and for the delta H also, you get this. You have this general equation for delta H, which is integration of Cp times dt. And because of the Cp is constant, you can just bring out the Cp outside, and then you get the equation of delta H equals Cp delta T. Okay. All right. So another type of process is what we call the polytropic process. So polytropic process is basically just the general term to cover all the types of processes that we have. Okay. So polytropic means turning in many ways. Okay. So in this case, we assign a general symbol ataupun parameter here, which is the delta. So PV to the power of delta is constant. And then TV to the power of delta minus 1 is constant. And then you have this for TP. So if we plot this, the different processes on PV graph, so you have the pressure here and then the volume. You can actually see for the different processes. Okay, first you have the constant pressure. So constant pressure, of course, the pressure is just constant lah, tak berubah, constant. So in this case, the delta is 0. Okay, so you can just substitute 0 dekat sini. Okay, so that means for the constant pressure, ini 0, so V tak ada lah. So of course, yeah, P constant. And then here you have T V power negative 1. So that means T over V. So T over V constant. And then So you can derive the relationship based on the values of delta. Okay. And then the second type is the isothermal. So isothermal, the delta is equal 1. So for isothermal, PV is constant. And then, okay, T constant. And then for the TP, 1 minus. Yang ini kita tak ada. Okay. Alright, and then for the adiabatic, you have the delta equals gamma. Okay, so you can just replace gamma here. And for any other values of delta, so the value can be anything in between gamma and 1. Okay, so for any other values, you can just put the value here and to get the relation, these relations.
Oh, this really?
Oh, another one is for the constant volume. So for the constant volume, the delta becomes infinity. Okay. Okay, example 1. Is this from the textbook? Okay. All right. So this is example 1 for ideal gas. 1 mole of an ideal gas with Cp equals 7 over 2R and Cv equals 5 over 2R expands from P1 equals 8 bar and T1 equals 600 K to P2 equals 1 bar by each of the following paths. Okay, A constant volume, B constant temperature, C adiabatically. Assuming mechanical reversibility, calculate the W, Q, delta U and delta H for each process. Okay. So just now, all the equations that I have shown you for the different processes, they are applicable for mechanically reversible process. I think you have learned about reversible and irreversible process in thermodynamics, right? Okay. So this basically means that if you reverse the process, then you will get 100% the same value. Okay. All right. So the solution for this problem, this example. Okay. So you are given Cp. This is the value of Cp, 7 over 2R, and then Cv, 5 per 2R. And then you have P1, 8 bar, P2, 1 bar, and T1 equals 600 Kelvin. Okay. So the first process is constant volume. Okay, so for the constant volume, so from this ideal gas equation PV equals RT, you can bring this, you can rearrange ya. So V R bawa dekat sini, T bawa ke sini, so you just left with the constant on the left side and you have T and P on this side. So in this case, the P over T ataupun T over P constant. Okay. Alright, so in this case, the question asks you to calculate the W, Q, delta U and delta H. Okay. So first you write the general energy balance, which is delta DU equals DQ plus DW. Okay, and then you can substitute dW with the negative PdV. In this case, because of V constant, then dV is 0. So this term here becomes 0. Okay, so you have du equals Cv times dt. Okay. So in this case, the delta U is equals Q, which is equals this here, integration of Cv times dt. Okay, so from here, okay, because kat sini kan you ada T1 and T2. So you need to know the value of T2. So how can you determine the value of T2 is from the ideal gas correlation tadi lah. Okay, because you have P over T constant. So you have P1, you have P2, you have T1. So you can determine T2. So in this case, T2 is 75 Kelvin. Okay, so you can substitute. Masukkan dalam sini ya, CV tadi is given ya, CV 5 over 2R. So you boleh buat lah. Okay, so just substitute 5 over 2 R times T2 minus T1. So this is the answer for delta U and also Q. Okay, negative 10912.13 joule. Okay, for delta H, you get from the equation, yeah, ini CP, integration of CP times dt. So you just substitute CP is 7 over 2R and then times T2 minus T1. So you get this value negative 15276.98 joule. Okay. Right, the second one is for constant temperature isothermal process. So again, you can start with the energy balance. Okay, in this case, you have the du equals Cv dt, which is equal 0. Okay, of course you can just use the previous equations that I show you from the textbook. Okay, you don't need to derive by yourself from the energy balance, but I like to do it this way because it makes me understand the whole thing better. Okay, so in this case the du or the internal energy becomes 0, and then dq equals negative dw, so equals pdv. Okay, so you can get the value of q with from the integration of p times dv. Okay, so in this case, this equals RT ln P1 over P2. So you just substitute values of R, T, and also the pressures. Okay, so you get 10373.09 joule. Okay, so this is for the Q and work. For the U and H, they are 0. Okay, for constant T. Okay, C for the adiabatic process. So adiabatic dq equals 0. So Q is 0 lah. Okay. And then from the energy balance here, dq is 0. So you are left with the dw only. Okay, and then from here you get this relation delta U equals W equals integration of CV times dt. Okay, so you just substitute, get this negative 5591.17 joule. Okay. For delta H, you get this from the relation between H and CP. Okay, so here you need to determine the value of T2, kan? So for the T2, you can get the value from the relation of this. You have this, mana tadi? Yang ini, this one, So you have P1, P2, and T1. You want to know T2, so you can use this. The last equation here. So you substitute delta with gamma for adiabatic. Okay. So the gamma you can calculate like this lah, yeah. So gamma is Cp over Cv. So you get this value. So you can substitute and you can get the T2 value. Before you can calculate the delta U and the delta H sebab kat sini ada integration with T. Yeah. Okay. Any questions? I hope I didn't go too fast.
So far okay, Doctor.
Okay, all right. So up until this point, you have learned about the ideal gas. In the next following section, I will show you the calculation for non-ideal gas ataupun real gas. Yeah. So ideal gas tadi is simpler because you have this relation PV equals RT. Okay, the general equation that applies for all types of gas is PV equals ZRT ataupun ZRT. For ideal gas, the Z becomes 1. Okay, and this ideal gas is valid for low pressure. Okay, so for the non-ideal gas, you ada value Z ni. Okay, so the Z value is less than 1. Okay, so it's from 0 until 0.9999 something lah. Okay, kalau 1 tu dia dah jadi ideal gas. Okay, so in this case, we can use the equations of state. Okay, which is developed from the PVT data. So remember last Sunday I showed you the graph, yeah, PVT graph. So you can see the line. So the line can actually be represented by the equations of state. And also we have the generalized correlations. Generalized correlations derive from the equations of state and also from the theorem of corresponding states. Okay. All right. So the equations of state, the general apa tu? This is the general term that we use to show that this is the equation to show the behavior of the PVT. Yeah. So under the equation of state, you have the ideal gas equation, which is the simplest equation, and then the virial equation. Last Sunday, I also showed you just a bit on the virial equation. Can remember when you have the term equals 1 plus something power 1 and then power 2, power 3. That is virial equation. Okay. And then the third one is the cubic equation of state. That's when you have the cubic term. Cubic ni maksud dia power 3 So V to the power of 3 ke ataupun P to the power of 3. So that is what we call the cubic equation. So under the cubic equation of state, you have this van der Waals equation, the Redlich-Kwong-Soev, the Peng-Robinson, and the generic, which can be applied for the calculation of saturated vapors or saturated liquids. Yeah. Probably you have heard about van der Waals before, right? And the rest of the other three types of the the cubic equation of state is basically comes from the name of the scientist that proposed or that invented the equation. Okay. All right. All right, so applications of the virial equation. So virial equation, something like this, yeah. So I think last Sunday I have shown you we can write Z in terms of the virial equation. So you have Z equals 1 plus B dash P. This is for yang the first one is what we call the two term, where you have the first term is 1 lah. And then you have the B dash P, this is the second term. So when you cut the virial equation just until the two term, the second term, then we call this equation as the second virial equations. Okay. And similarly, you can also have up to 3 terms yang bawah ni. Okay. So this is what we call the 3-term virial equation ataupun the third virial equation. Okay. So for the first equation, yang ini the second term or the 2-term virial equation, it is applicable for low to moderate pressure. So normally we consider pressure below 15 bar. So you can look at this graph. The x-axis is the pressure in bar, and then the y-axis is Z. Okay. So untuk yang the first the two-term virial equation tu dia valid lah, yang is shown by this color here. Okay, so this light purple color ni menunjukkan where the second virial equation is applicable. Okay, so you have you can either write the second virial equation using the B dash ataupun the B. Okay. Okay. So the B dash and the B, they are apa tu, coefficient. So dia it depends on the substance type, and also it's a value of temperature. Okay. Now the second one, which is the 3-term virial equations, they are valid at slightly higher pressure compared to the first one. Okay. So this can be applied to pressure up to 50 bar, but must be below the PC, critical pressure. Okay, so they have a wider application range for the pressure. Okay, so the 3-term virial equation is shown here. Okay, you can either write it in terms of the B dash, C dash, or B and C. So the relation between B dash and B is this. B dash equals B over RT, and the C dash is this. Okay. All right, example. This is the same example as your textbook, example 3.8, page 89. Okay, reported values for the virial coefficients of isopropanol vapor at 200 degrees C are B equals negative 388 centimeter cubic per mole, and then C is negative 26000 centimeter power 6 per mole square. Okay, so calculate V and Z for isopropanol at 200 degrees C and 10 bar by the ideal gas equation, B virial equation to two terms, and C truncated virial equation to three terms.
14, 15, 16, 17, 18, 19, 20, 21, 22.
Okay, right. Sorry, Okay, so just now I mentioned to you the values of B and C, they are substance specific, and they depend on the pressure, the temperature. That's why you can see here. So yang ini value untuk B dengan C ni, they are only valid for this isopropanol at 200 degrees Celsius. So if you change the temperature, the value will change. If you change the substance, it will also change the values for B and C. Okay. So now you need to calculate V and Z. Sorry. Oh, okay. I think I only have here the solution for C. Okay, anyway. The calculation for A and B is actually straightforward. Okay, so for A, for the ideal gas, you can just use the PV equals RT. Yeah. So PV equals RT. And of course, the Z is 1 lah dalam for the ideal gas, Z is equals 1. So you can calculate V from this. So V equals RT over P. You just substitute the temperature and the pressure. Okay, so you can get the answer 3934. Yes, I will just write the answer from the textbook. So V equals RT over P, which is equals 3934. Okay. All right. And then for B, virial equation to two terms. So this one you can just use the the virial equation, equation 3.38. Yang ini lah. Okay. This one. Right. Yes. You can use this equation 3.38, 3.39 to get the values of V and Z. Yeah? So the V is you can actually directly apa tu calculate for Z using this first term here, ataupun if you want to calculate for V first, then you need to rearrange this equation to bring V forward, V equals something. Because if you look at the solution from the textbook, dia cari jawapan untuk V dahulu. Okay. So V is given by this. Okay. So this is 3546. Okay, from the V value you can get the Z. C equals EV equals RT. Okay, RT. So you boleh dapatkan lah Z. So Z is 0.9014. 9014. Okay. Okay, just take note the value of Z, dia mesti below 1, below 1. Yeah, if let's say you calculate, you get the value of Z 1 point something, then that maksudnya calculation you salah lah. Okay, so remember the value of Z must be below 1. Okay, alright, so untuk yang C, truncated virial equation to 3 term. So this is you have to use the 3 term virial equation, which is this one. So you have this equation for Z kan. So you can substitute. Macam mana nak dapatkan equation yang bawah tu is you simply substitute into the PV equals ZRT. So V equals saya buat macam ni, RT over P times Z. So yang Z ni kita substitutekan lah yang ni. Okay. That's why you get this lower equation here. Okay, so in this case, when you have this kind of equation, you want to get the value of V kan? You punya left hand side here ialah V. But at the same time, you have V in your right hand side. Dalam equation ni pun ada V. So in this case, you can solve it using iteration. Okay, ataupun trial and error. Okay, so for the iteration, you can start with V, the value of V for the ideal gas. So tadi kita dah calculate untuk A kan. So A tadi ideal gas value 3934. So you can start with this 3934, substitute into this equation. Yang lain-lain tu you substitute jugalah. You have the R, P, and then the B and C given from the question, and you substitute the value of V to get a new V. So this one we label as V1. Yang initial value tadi kita guna V0 ataupun V0. Okay. So you get V1 as this. So now you have this V1, you substitute again. Masukkan balik dalam equation ni to get V2. So you repeat the process until the values do not change. The values remain constant. So in this case, after 5th iteration, you get the constant, the value is remain the same. So in this case, this is the answer, 3488. So you get V 3488 centimeter cubic per mole. So you can calculate for Z. So using this, Z equals PV over RT, you get 0.8866. Okay. Faham tak kenapa kita nak kena solve guna iteration ya? Sebab you ada the same parameter on the right hand side and then on the left hand side. So you definitely cannot solve it just straight away. So you kena pakai iteration like this lah. Okay. Alright, so this tutorial I'm going to skip. Maybe I will give you in your assignment later. Okay, so it's very similar. You are given this values for B and C, and you need to use the virial equation to solve the nak calculate work, yeah. Alright. Okay. Okay, so far ada soalan? Any questions? So for the virial equation, you need to know the values, the parameters of B and C. Okay. So the values for B and C, they are substance dependent and also temperature dependent. Okay, next is the cubic equation of state. Mungkin I think this part is probably slightly difficult for you. Okay, it's slightly more complicated compared to the virial equation. Okay, so cubic equation of state. All right, so cubic equation. This is the simplest equation capable of representing both liquid and vapor behavior, but not for dual phase condition. Okay, and it is more accurate for a wide range of T and P. So this is the general or the generic equation for the cubic equation of state. So you can see the term V kat sini kan, and then you have V and then V squared here. That's why I said just now, when you have bila you darab sini V times V squared, you get V cubic power 3. That's why we call it cubic equation. Okay, so in this case, B, theta, kappa, lambda and eta, they are parameters which is general depending on the temperature, and for mixture, it depends on composition. Okay. So from the first equation, we assign these equations to the general or the generic cubic equation to get this new equation here. Why do we want to change this form here? Later you will see that these are the values that you can get, the constant, the values or the parameters that you can get from a table later. Yeah, so that's why we want to change this form, this equation, to a more general form that can be used, where the values of the parameters can be derived from the table later. Okay, so here you have P equals RT over V minus B, and then you have this epsilon and then sigma. Okay, and then here A, yang ini A bukan A darab T. This is A in a function of T. Okay, so here epsilon and sigma are pure numbers, the same for all substances. Okay, A function of T and B are substance dependent. So this is the equation for A. So A equals A. It's a bit confusing. Oh yeah, okay. So A in a function of T is equals A in a function of TC, critical temperature, times alpha, which is in a function of TR. Okay, and then this is the equation for A in a function of TC. Okay, so you have a lot of equations here. Don't worry, you don't need to memorize the equation. Okay, you can refer to your textbook for the equations. Okay, so this is the equation for A in a function of TC. And then you have the equation for B, which is a function of this omega, yang ini simbol omega. And then you also have this you also have this symbol TR and PR. Later we will see why we need this TR and PR. Sebab nanti later when you refer to the parameters, you need the value of TR and PR instead of the absolute pressure or the absolute temperature. Okay, so TR is defined as the temperature or the absolute temperature divide with the critical temperature, and PR reduce pressure is the pressure divide with critical pressure. Okay. All right. Okay, so this one, I normally during face-to-face class I show you the step by step how you derive the equation lah. But you know online class ni saya rasa macam I think you pun tak pay attention sangat when I do the derivation. So I will just show you the final equation and just slightly explain to you how they derive the equation. Okay. So when you rearrange this equation yang mana tadi so yeah. If you start from this equation 3.442 and you substitute all the parameters here with yang ini A tadi you substitute, and then the apa tadi PC, the B, and so on, you can actually get to this point where you can get this equation V in terms of V, and then TC, PC, and then you can rearrange it so that it equals 0. Okay, so this equation here, it actually explains the line on the PV graph. Yeah. Remember last time I showed you the PV graph. So you have this line yang showing the isotherm tu kan. You have like macam curve like that. So this curve, yang curve dash line warna merah ni, they can actually be represented by this equation. Okay. And then so in this case, you have the PC and the TC. So PC and TC, they are the pressure and temperature in critical point. And then the A and B, they are the constants. Yeah. So the B and A constant, yang ini pun adalah cara macam mana dia dapatkan the equation. They can actually be derived from this equation. It's actually based on the shape of the shape of this graph kan, yang you have this like dome, bukan dome, bell shape melengkung ni daripada bawah ke atas. So you can actually find the critical point here. This is the C. And then when you do when you have the differentiation kan, bila dekat critical point ni, when you do the dy dx, it should be equal 0 lah at this point. So that's how they can, get the values for A and B like this. Okay, eventually we end up with this equation for A. You can calculate A based on the value of TC and PC, and then also for B is also based on the TC and PC. So that means A and B, they are values that are depends on the type of substance. So substance dependent, because different substance you will have different TC and PC. Betul tak? Okay. So it just depends on the type of substance. You can know the TC and PC, and you can calculate A and B. Okay. Alright, so the first type of cubic equation of state is the van der Waals equation. So this is the simplest form of cubic equation of state. So in this case, the equation of the generic equation of cubic equation can be reduced to this equation. Okay. Alright, so in this case, you are only left with, okay, the first term yang RT over V minus B ni sama, still remains the same. The second term is reduced to this only, okay? So you have A over V squared. Okay, and then the A and B can be determined from this equation. Okay, so this is the van der Waals equation. Okay, and then for A and B, they are positive constant. So they are positive constant, yeah. So they must be larger than 0. And if A and B equals 0, if A and B equals 0, you can this equation will become the equation for ideal gas. Okay. Alright, so the second type of cubic equation of state is the Radley-Kwong equation. So in this case, the first term still remain RT over V minus B, but here on the second term, if you compare with the van der Waals, dia ada sedikit penambahan kat sini. So you have A in a function of T, and then over V times V plus B. Okay. A dengan B ni dia masih sama lah tadi, this this one, B equals omega times RTC over PC, and then this is for A. Okay, so here you have this equation in term for P, yeah, so P equals something. So now we want to we want to solve the equation for V, yeah. So in this case, we rearrange the equation. You boleh darabkan bahagian yang bawah ni darabkan ke atas and then rearrange to get this equation here. So V equals to 0. And then this is the general method. Sekejap I forgot. Oh, okay. Okay, so sekarang ni you have this equation for P, right? But if let's say you want to solve for V, so you need to rearrange the equation. You need to bring the V forward so it becomes V equals something lah. Okay. So in this case, after rearrangement and then you solve using the cubic equation solver, you will get two types of root, yeah, two types of solution for the V. So the first one is the V for gas phase, and then you have the V for liquid phase. Okay, because how to say, when you refer back to the PV graph, actually this line yang saya tunjuk kat sini, this is from the PV graph. Okay, so you have P and then V. So there is this region here when you have this liquid, this is 100% liquid, and then bawah sini under the curve, in between ni you have the liquid plus vapor region, and then you have the 100% vapor region. Okay, so at the given pressure, let's say you have P here, this horizontal line yang biru ni is showing the P. So you can have the V for gas phase and also for the liquid phase at the specific pressure. That's why you sometimes you want to know the volume for the pressure, the liquid and also for the gas. Okay. Don't worry too much about this equation. Yang ini dia specifically solve for the Radley Kwong, but actually later we will use a general equation for the cubic equation of state that you can use not only for Radley Kwong but the other types of cubic equation as well. Okay, so next you have the Radley Kwong Soev ataupun Soev Radley Kwong. Sometimes we say SRK, in short. So the SRK, and then this is the Peng-Robinson. So you can see that the second term becomes more complicated with more number of variables. Okay, you have this alpha, okay, here. And then untuk PR ni, kat bawah ni dia bertambah lagi, this term. Okay. Alright, so you have this alpha. So alpha is given by this equation. Okay, alpha equals 1 plus benda-benda tu, and then you have the ini. Oh, okay. I think because we have another equation for alpha. Yang ini, saya takut you confused. Maybe we can just refer to the one in the table lah. Okay, tak apa. Just take note that for the SRK and the PR, you have this new parameter which is alpha here. Okay. Alright, so ini table yang saya mention just now. So based on the from the generic ataupun general form of the equation, you can actually get the values for the parameters, and then you can put inside the general form of the equation to get the whether it becomes van der Waals ataupun Radley Kwong ataupun SRK or PR. Okay. So okay, this one. So you have this equation 3.42 tadi. Is this better or? Okay. Tadi you have this general form of the cubic equation of state in terms of P yang ini. Let me just write down here. Yang ini so this is equation 3.42. So from this general equation of state, okay, let's say you nak gunakan untuk van der Waals, so you can just substitute kat sini So untuk van der Waals, sigma dia ini 0. epsilon pun 0. So you are only left with V squared. Yang A ni, untuk A dia ada equation dia tadi. So A is ATC times alpha TR. Okay. ATC tu dia adalah chi R squared TC squared over PC. Okay. Mana nak tulis ni? So ATC is this one, R squared AC squared over PC. Okay. So that's why you need the yang ini okay, katalah tadi you want to use this equation, you want to apply the van der Waals, okay? So okay, AT, untuk AT you have this equation, AT equals A in a function of TC times apa ni tadi, alpha TR. Okay, so ATC is given by this. So ada this parameter here, chi So you need to get this chi. So untuk van der Waals is 27 over 64. So you just replace lah, substitute dekat sini. Okay, and then the R, the TC, PC. So TC, PC ni you can get the value later I will show you, okay, but this is substance dependent. Okay, so if you are given the name of the substance, kalau you tahu okay methanol, then you can get the value for TC and PC. Okay, so you need to find the ATC and then you need to find the alpha TR. Okay, so the alpha TR is given here. Untuk van der Waals, alpha TR dia is equals 1. Okay, yang ini salah this is supposed to be alpha, saya dah cancel kat sini. And then for Bradley-Kwong, alpha TR is equals TR to the power of negative 1 over 2. And then for SRK and PR, alpha dia is given by this equation below ni. Okay, so the alpha for SRK is this 1 plus bracket 0.485. Please check your textbook the actual values, sebab because I cannot edit this table, dia dah it's using the previous version of math punya equation. I cannot change it. But okay, so the values here is supposed to be 0.48 untuk SRK. You can check from your textbook, okay? So this is table 3.1, page 98, okay? And then here you have plus 1.578 omega. This small bentuk macam W ni is actually small omega. This is a Greek letter. Okay, omega, and then here you also have omega. So yang omega ni, this is another parameter that is that depends on the substance. So kalau you tahu apa nama substance tu, you can find the value of omega. So later you can actually find the values for omega, TC and PC from appendix C appendix B. Okay, that's why you need this textbook lah, for you to refer to the appendix. So appendix B ni, properties of pure species, it will give you the values, the critical parameters and also the omega. Okay, so if let's say you refer here table B1, this is page 680. If let's say you're given methane, so the first substance here is methane. So methane, you can find the molar mass, and then this is the omega, the TC, PC, ZC, VC, and also the TN. TN is what we call the normal boiling temperature. Okay, so the normal boiling temperature is defined as the boiling temperature at the normal atmospheric pressure. So kalau water tu at 1 atm, the boiling temperature is 100 degrees C. Itulah. Okay. So this is the use how you can substitute the value from the table here to get to based on what you want. So whether you want to use the van der Waals ataupun Rayleigh Kwong or the SRK or the PR, you need to, get the values of the parameters from here. Okay, so just now, you can have this equation, the generic cubic equation in terms of P equals, ya. Yang ini P dia dekat depan. Tapi, but sometimes you, macam nak cakap Kalau P dia dekat depan, meaning that you have the value of V. You are given value of P, you are V. You are given value of V, you are given value of T. You can calculate for P, betul tak? Tapi in real cases, most of the time you have the value of P and T, and you want to know V. Sebab apa? Sebab in real life, you can measure T and P much easily compared to V. Sebab temperature, you can just use thermometer, for example, kan? And then for pressure, you can measure using the barometer ke ataupun using the manometer ke. So it's much easier to be measured compared to volume. Kalau volume ni sometimes macam mana you nak measure volume, betul tak? So most of the time you have the data of P, pressure, and T, temperature, and you want to calculate for V. So it's more useful to convert the equation so that you put the V dekat depan lah. So you want to get this V equals something. Okay? So again, remember, because it's a cubic equation, you boleh dapat theoretically sebenarnya you boleh dapat 3 root sebab dia V kuasa 3, betul tak? V to the power of 3, you can get 3 roots. Okay, kalau V kuasa 2, you boleh dapat 2 root. Tapi, okay, going back to this PV diagram again, okay. So at the same time pressure, P, katalah you tengok dekat line hijau ni. So at the same pressure, if you increase the volume, ya, daripada volume rendah kepada yang tinggi. So first you get the liquid, okay. So you get the liquid, and then you get the liquid plus vapor, okay, and then you get the vapor only. So theoretically you ada 3 jenis volume lah. So volume of the liquid only, volume of the liquid plus vapor, and volume of the vapor only. Tetapi in actual case, in real case, this volume of liquid plus vapor ni, dia very unstable, and it's not really, how to say, it's not very stable, and sometimes it's just like a very short transition. So in most cases, kita tak concern dengan volume yang tengah-tengah ni. So we are only concerned with the volume of the liquid only and also the vapor only. So we have these 2 types of roots, what we call the roots, yeah. So the first one is the vapor or vapor-like roots of the generic cubic equation of state. So tadi from the equation of P something tu, kita rearrange dia supaya kita boleh dapat V equals something. Okay? So you get 2 roots. The first one is the vapor or the vapor-like root. So again, kalau kita, if you refer back to this graph, so yang ini kita panggil juga largest root. Sebab apa dia largest? Sebab if you see here, kat sini kan V dia besar lah. Yang paling besar V dia kat sini. And why we call it vapor and vapor-like? Sebab sometimes the line, okay, if we trace this blue line, sometimes this line that intersect with the actual the liquid volume punya line yang merah ni, sometimes dia dekat at the specific pressure, dia dekat dalam curve ni tau. So in this case, dia is not exactly vapor, but what we call vapor-like, because it's it's not above the saturated vapor punya line. It's under that. So it's not exactly vapor, but it's vapor-like. Okay, so whether it's vapor or vapor-like, it depends on the pressure. Okay, kalau you increase the pressure, if okay, referring to this green line, you increase the pressure somewhere here. So maybe dia punya vapor dia akan jadi 100% vapor. So it's 100% vapor lah, it's not vapor-like. Okay, so it can be vapor or vapor-like depending on the pressure. Okay, So in this case you have this equation. Again, dekat sini you akan nampak lah ada epsilon, ada sigma. So you have to refer to this table again. Okay, table 3.1 to get the values for the sigma, epsilon dan sebagainya. Okay. Alright, so alright, so in this case, just now, okay, of course we can have this equation for V, tapi sometimes it's you know, to make things simpler, you know, researcher ni dipandaikan, dia nak mudahkan hidup dia, so sometimes we change the equation a bit, okay, so that we can you know, get the parameters that we can get from the experiment contohnya, right? So in this case kita ubah equation tu from V equals to Z equals. So after rearrangement you can actually get this equation. Okay, Z equals 1 plus beta plus Q beta, okay, times this. So this is equation 3.52. So this applies for the vapor or vapor-like root. In other words, the largest root. Sebab tadi dia punya V yang paling besar. Okay. So in this case, you can first calculate Z using this equation. Okay, sebab tadi kan saya cakap kalau dia ada dekat kanan ada, dekat kiri ada, you have to do iteration. So in this case, you have to do iteration. We start with the largest possible Z, which is 1. Okay, so you start with Z, 1. You substitute into this, yang the rest of the parameters you get from the table. Okay, you calculate the new Z, and then using the new Z value, you substitute again to this equation until you get a converged value. So the final value doesn't change much. Okay, so that is your final Z, and you insert this Z into this equation, V equals ZRT over P to get the V. So this is what we normally do when you want to calculate the V volume. Yeah, you calculate the Z first. Okay, so the second one is the liquid or liquid-like roots. So tadi saya tunjuk dalam PV graph tu, you have the volume for the liquid kan. So that is the smallest root, the smallest volume. Okay. So in this case again, kita substitute, kita rearrange the equation so that you get Z equals something. Okay, so in this case, after rearrangement, you get this equation Z equals beta plus blah blah blah. Okay. Right, so similarly, we solve for Z first using iteration. Okay, but in this case, we start with the smallest possible Z, which is Z equals beta. Okay, so untuk volume root tadi kita guna Z equals 1 as the initial value, but for the liquid root we use equals beta. But the rest of the process is the same. Okay, you substitute, start with the Z naught equals beta, you get new Z and then you insert again, calculate Z again sampai value dia converge. Okay, so once you get the final Z, you insert into V equals ZRT over P, you get the V. Okay. Alright, example. So sebenarnya equation yang you perlu ingat ataupun kalau ingat by saying ingat bukanlah saya suruh you hafal, but you must know that this is the equation that you need to use. Okay, is equation 3.56, okay, for the liquid root, and 3.52 for the betul ke? For the apa tadi, vapor root. Okay. Okay, example. So I think you will understand better if you look at the example. So calculate Z and V for ethylene at 25 degrees C and 12 bar by the following equations. A, the Radley-Kwong equation. B, the Soev-Radley-Kwong equation. And C, the Peng-Robinson equation. Okay, saya dah tunjuk sebenarnya jawapan dia dekat sini, the solution. Alright. So, Okay, your species ataupun your substance here is ethylene, and then you are given the temperature 25 degrees C, and then the pressure is 12 bar. So based on this information, you can find the Z, compressibility factor, and also for V. Okay. Okay, so sekarang ni. Now, first, first you have this species, the substance which is ethylene, and then the given temperature 25 degrees C, which is equals 298.15 Kelvin, and then the pressure is 12 bar. Okay, so first you need to find the critical parameters, yeah. So ethylene, you need to find the TC and PC, and also at the same time you find the omega, sebab omega tu nanti kita perlukan untuk the SRK and Penn-Robinson punya calculation. Okay, so macam mana nak cari TC dengan PC dan omega, you refer to appendix B. Tadi saya dah tunjuk So, okay, you just open the appendix and then you find the species, substance name is ethylene. Okay, ethylene dekat sini, somewhere here, somewhere in the middle, here. So you just read lah the value. Ethylene omega is 0.087, and then the TC is 282.3. Okay, saya dah tulis kat situ, 282.3 Kelvin. And then the PC is 50.40 bar. Okay, so you just write down the values, okay? And then okay, and then here I also calculate the TR and PR. Kenapa saya calculate? Sebab nanti dalam equation ni nanti untuk beta dengan Q ni nanti, you need the TR and PR value. That's why saya kira siap-siap dulu lah. So I just calculate first. TR is T over TC. Okay, so substitute dapat ini. PR is P over PC. Okay, so first, sekarang ni you have to determine first whether this ethylene at this pressure, at this temperature, whether it's a gas or it's liquid. Okay, so we can compare the temperature. So the given temperature here is 25 degrees C ataupun 298.15 Kelvin. So it is higher than the critical temperature TC, kan? So 298 is higher than 282. So in this case, definitely it's a gas or vapor. So you can use the Z for the vapor route. Ya, sebab tadi you ada Z dua kan, ada vapor route dengan liquid route. So mana satu nak guna? You kena tahu dululah sama ada substance tu dalam liquid ataupun dalam vapor. Kalau dalam vapor, you guna equation yang vapor route. So we use the Z for the vapor route, which is this one. Okay, equation 3.52. Okay. So from here, you need to determine the beta and then the Q. So beta, this is the equation and this is the Q. And then you need to get the value for omega. Yang ini, this is large omega. And then PR, TR. Yang ini, you have the chi and then the alpha and the omega and TR. So kena refer, you have to refer these values, refer the table for the values. Okay, so for the Radley-Kwong, omega, large omega is 0.08664 and then chi is 0.42748. And then the alpha TR is TR to the power of negative 1/2. Okay, so just substitute everything into the equation. You get beta, you get Q. And also you need epsilon and alpha. This is from the table. So you substitute into the equation. Okay, we have to solve by iteration. So we start with Z equals 1. Okay, after substitution, I get Z, the first Z, Z1 equals 0.93414. And then repeat, sampailah value the converge, meaning that the last two values, when you take the difference, it doesn't differ much, okay? So in this case, I take the final value as inilah 0.92. I think if you do the calculation is 0.92777, but Probably that's the answer given by the textbook. Sekejap, Is this? Sorry, yang ni tak ada dalam teks. Not from the example. Probably from the problems at the back. Okay, never mind. So you can get the value of z, yeah. 0.9278 or 77 macam tu, okay. So finally you just substitute the value for the value of z here in this equation to get v. So you get v 1916.48 centimeter cubic per mole. Okay. Now for SRK, sama juga prosedur dia. You have to get the parameters from the table, but it's just for the SRK, the alpha value becomes a bit slightly more complicated because you ada this equation, yeah. So this equation, the alpha now is a function of TR as well as omega. Okay, so omega tadi kita dapatkan from appendix. So you just sub omega and then the TR to get this value. And then you get the Q. Okay, and you get the Z solved by iteration. Finally, you get the V. Sama juga. Okay. PR pun sama juga. First you calculate the alpha and then you get the beta, the Q. And then you substitute into the Z solved by iteration. Okay, get the final Z and then you get the V. Okay. So now you can compare the values of V from the different types of cubic equation of state. Yeah. So tadi, PR ni you get 1900.6. The SRK you get 1918. And then the RK you get 1916. Okay. So normally the values for RK and SRK, they are very close, very similar. Okay. And then the PR, normally it will give you the lowest ataupun the smallest value of V. As you can see here. Yeah? Okay. So that's how you find the volume, the specific or the molar volume from the Z. Okay, so the Z equation, first you need to know whether the substance is in liquid or in gas, in vapor. Kalau di dalam vapor, you use the equation Z for the vapor root. Kalau di liquid, you use Z for the liquid root. Okay, from the Z, you get the value of V. So untuk solve Z tu, it depends whether it's radical ataupun PR ataupun SRK. So the parameters will be different for the different types of cubic equation of state. Okay. Any questions at this point? Ada soalan? Oh, okay. Sekejap. Okay, so untuk cubic equation of state tu dah basically I dah cover lah semua. Okay. So remember again when we mention cubic equation of state, you have the power tree. Okay, that's why we call it cubic equation of state. So for the cubic equation of state for the fluid, you have apa tu tadi, van der Waals, and then you have the radical, you have the SRK, and then the Penn-Robinson. Okay. Dan dalam test ataupun final exam, normally kita akan we will specify. Okay. In the question itself, we will indicate. Okay, we will specify. Okay, use this Bradley-Quirk equation. Use Penn-Robinson. Okay, because if we don't specify, then of course we can ask you to do the calculation using all the equations and then you compare. But normally memang kita akan specify. So don't worry which equation to use. Of course daripada segi theoretically tu which equation suit at which temperature or pressure tu theoretically dia ada lah. Okay, tapi to save you the hassle, normally kita akan terus ask you which using this equation, using PR or using red Wong dan sebagainya lah. Okay. So okay.
Doctor,
Uh-huh.
may I ask for the tutorial just now, right?
Mm-hmm.
Boleh kami find V first ke? Then balik find Z.
Boleh juga. Mm-hmm.
So just use the same equation, which is the V1, and then calculate. After that, just use the V equals to ZRT divided by P equation to find Z, right?
Mm-hmm. So you can start with the largest V possible, which is the ideal gas value lah.
Okay, thank you.
Okay. You mean yang tadi yang kalau if you want to use the Redley Kwong, the PR and so on if you want to start with you want to find the V first, is that your question?
I mean, just now Doctor used Z, right, and then use iteration, right?
Mm-mm.
I mean that part, the iteration part, can I use the V and then I do iteration for V? I find V, right? And after that, I find a convergence for V, and then the V, and then use the equation find the Z. Can
Yes, you can, but kalau dalam yang yang awal-awal tadi saya tunjuk you three term kan, three term equation. Yang itu you can start with V, iteration for V. Tapi untuk yang apa tu, cubic equation, sekejap mana equation dia? Yang ini this one. This one. You can actually use V, I mean do the iteration for V, but you need to use this equation lah yang ini. Okay?
Yeah. This one. So
yeah.
can use this one and find V first lah. And
Yes.
then iteration find Z.
Boleh, yes.
Okay, thank you, Doctor.
Okay, so the next part will be on the generalized correlation. So I think I better explain the next time sebab nanti kalau saya explain sikit nanti lupa kan. I think better just save for the next time. We still have some time. Probably you can try this tutorial too. Yeah. Okay, so very similar to the example just now. Okay, it's just that we change the species, the substance type. And then you have the temperature and the pressure. Okay, so you need to calculate Z and V. Okay, so same procedure again. So you find the critical parameters TC, PC and omega from the appendix. Okay, and then you can use the equation for Z if you want to use the Z. Okay. Oh, okay. First, you need to determine lah whether at this pressure, at this temperature, ethane is in liquid or in gas. Okay. After you determine liquid or gas, baru you boleh tahu lah which equation to use. Alright. Oh, before I forget, for those of you yang tak ada lagi textbook, I have uploaded the appendix in e-learning. Yeah. Sekejap let me share the e-learning page. Sekejap. E-learning. This is, oh sorry. So if you don't have your textbook textbook yet, you can refer to the e-learning for the appendix ya. Sebab you memang kena refer to appendix untuk dapatkan the parameters, the values ya. Okay, yeah, okay, this one. Okay, you can see my screen, right? Dekat sini So under the general, on the top page you have the general and then the description, CO, CLO semua tu. Kat bawah ni, just below the course information you have these appendices, okay? So you need to refer to appendix yang semua yang berkaitan tu saya dah upload dekat sini lah. So appendix A, B, C, E and F. Okay, so now you have to use appendix B, properties of your species. So if you click on the appendices, appendix B. Alamak, download dulu. Okay, tak apa. Alright, so yeah, if you open appendix B, properties of your species. Okay, so you can see that, right? Okay, so you have to refer to this appendix for the apa tu? All the constant, the critical parameters, yeah. So just now you have the ethane. Okay, so you need to take the values for ethane, yeah. This is the omega, yeah. 0.1, and then you have the TC here in Kelvin 305.3, PC for 48.72 bar. Okay, so you have to take this values lah before you can do the calculation. Okay? Boleh Okay, so please try the tutorial. Kena cuba kira sendiri kalau you tak try, you tak tahu macam mana, how difficult it is to get the iteration. Sometimes students, okay, dia nampak when you see me do the calculation, you macam okay lah, boleh buat kan, senang je. Tapi bila you try by yourself, you baru tahu macam mana susahnya nak buat iteration tu, you know. Okay. And I have included the solution in the slide here, so you can check. Adakah jawapan dia semua? Let me check again. This is the slide. Yeah, I think I've shown here. Okay, first you need what you need to do in step by step. So first you need to find the critical pressure, critical temperature, and then the omega, from appendix B. And then second step is you need to find the TR/PR, and then the third step you need to calculate Q, beta, and alpha, And then the fourth step is the iteration, you solve for Z. And finally, you can get the V from V equals ZRT over P. Okay. So this is the answer for red liquang 2555 centimeter cubic per mole. Okay. And then this is just showing you what happens if you use the equation for saturated liquid, for liquid, You can see that the volume is much smaller compared to the volume of of gas. And this is of course macam itulah kalau you tengok graph tadi pun, the volume for liquid must be smaller than the volume for gas. Okay, kalau you dapat liquid tu lagi besar, that means your calculation is wrong somewhere. And then if you compare using the different equation, the top value here, EXP, this is the experimental value. Yang ini saya dapat from the textbook lah. Okay, the experimental value is 2483. And then if you use van der Waals, you get 2667. Redliquon 2555, 2555. SRK 2520. And PR is 2486. So in this case, the Penn-Robinson equation is the most accurate, or the closest with the experimental or the true value. Yeah. Okay, so please try by yourself calculation using the Redliquon, SOF Redliquon, and also the Penn-Robinson. Okay, so any questions? Kalau tak ada, I think we can stop here. And then next week we can continue with the generalized correlations. Okay, so remember again, untuk chapter 3, you punya aim ialah you must be able to calculate the volume. If you are given the pressure and temperature, you should be able to calculate the volume ataupun V, molar volume. Okay. Ada soalan?
Tak ada.
Tak ada, okay. Alright, so thank you very much. I will see you next Sunday lah. Okay? Alright, so nanti recording ni saya akan share dalam e-learning. Okay? Alright, so thank you everyone.